Welcome all of you. We are going to change the topic. It's going to be about processes and threads. Before I start, maybe I will give a brief overview of about processes and threads, which you might have already learned in your operating system courses. Then we will go into the details of how does Python handle it with the help of course, operating system underneath. So today I'm going to give just an overview of what are the different methods, functions we can use and how to create threads. And then maybe next week we can go a little more details about multi-threading application development using in Python. Okay. So maybe I'll use the slides to give you the overview, and I can add anything additional information that is needed. So all of us in the operating system course in your bachelor's have learned about processes and threads. Basically, what does it mean? Before I show this picture, what is a process? It's a single entity of execution, a sequence of execution, maybe doing a one particular type of a application. Okay, maybe a PPT, a PowerPoint. If I am opening, that is a one process. Now, how does the OS maintain it? Now we need the help of OS for a process to be alive, and you know that it goes through different states, process states like ready, then running, then blocked, then suspended, and then maybe finally getting killed. So there are different states of the process. So every operating system maintains a PCB, which is process control block, which has all the information about the process. Now, what are the information we need? We need, if suppose a process have opened some files, open files are to be there, and we need, if it has asked for some input, or if it is connected to a standard input, maybe expecting a keyboard entry, then there should be a socket or a pipe connected to that, and then we will be the process, if it is waiting for a particular input, or it is displaying something, if it is talking to an external network, then all these things need to be connected. So the state of a process means OS maintains all this information in the PCB. Apart from that, it also maintains the state of a process, which is like running, ready, and then running, and then blocked, suspended, or waiting for something, or it is sleeping. So there are so many states a process can get into based on what the process does while it is alive and running. Now, when does the process run? All of us are aware it has to be in the CPU for a process to run. So when assuming that we have a single CPU, then there can be only one single process that can run at a particular time. But we get a multi-threading or multi-processing behavior because we stop the process for some time and then allow some other process to run on the CPU, because we are expecting it to run, or we expect it to give the output of the processes. We are not at a place where we don't understand, or we don't maybe even sense it if the process is not running for a while and something else is running. We still feel that we are getting the equal amount of time for our process, right? Like for example, this PPT is not run always on the CPU. Whenever I am writing it, maybe it is not taking the input and then giving us an information, feeling that it is running continuously, but it may not be running because there are other processes have to run, interrupts have to come, and device drivers have to run. So all of them are fighting for the CPU, and process is one of them. Multiple processes are also fighting for the same CPU, which you might have all studied about scheduler, which does all that. Now, finally, when a process has to come into the CPU and then goes out of the CPU, we need to maintain the state of the, not only the state which I mentioned about running and then ready, that is our different state, but this is a context. Maybe I can call it as a context. Now, what is the context of a process? It is the values of all the registers in the CPU, as well as if it is using the MMU, even that contents, because this process may be having some part of the main memory reserved for it. So all the mapping of the virtual memory to the physical memory will be different for different processes, and the MMU content also is part of the context of a process, because they may be lying in a different part of the memory, and each process occupies the main memory at a different points in time, and we need to maintain the state of the mapping, and which may be changing also, because if a process goes out of the memory, if it is swapped out and it goes into the disk and comes back to the main memory, it may come to the different location in the main memory. In that case, the mapping between the virtual memory address and the physical address will change. So MMU contents also will change if the processor's image moves within the main memory. For various reasons, main memory is also is a limited resource, so OS may decide to pull it out of the main memory. So that also can happen. So a context of a process includes the CPU register contents as well as some part of the MMU registers and any other files it has opened. Then it may be lying in the main memory somewhere, and that information about file which the process is handling, all that are maintained. Now, when a process is out of CPU and something else is running, the OS gets a control of the CPU and copies all the contents of these registers into the context, which is a part of the PCB itself. So it maintains the information about the context of the process, and then whenever this process has to come into the CPU again, these register contents are copied back. The other CPU starts off from where it left prior to the scheduler coming and then pulling out the process from the CPU. So all these things are happening at the process level. Now there is a possibility that we have multiple CPUs, multi-cores there, multiple cores, then core 0, core 1. Then each of the cores can run one process. It can be P1 and this can be P2. That means OS may decide to run in one of them. Maybe it is sometimes OS is reserved for only one core. It will not be running on the other core. But there is possibility that even a OS code also can run on both the core. In that case, whenever the OS has to schedule a process, and if it decides to remove this process which is running on this core 0, then it does the same thing that I mentioned on this CPU and copies all the contents into the PCB, which is part of the OS data structure, and brings in some other process from the ready queue, whatever it's available. Now, what is the difference between a process and a thread? Now, there is what happens in this scenario when you have a process context P1 and P2. If I call them as processes, the context switch is actually very time consuming, because it has to, as I mentioned, it has to do a lot many things to bring a new process into the CPU, because not only the CPU content and some MMU content, because there are two different processes, they don't have access to each other. So P1 is lying here, suppose, and P2 is in the main memory. This is the main memory, and then P2 is reserved in the main memory, this region. This process does not have access to this process, so they need to be protected. So the MMU, memory management unit, needs to have the limits of where this process access stops and where exactly these processes start. So they need to maintain a different set of MMU content for each of those processes. So when we are saving or when you are switching from one process to other process, there is a lot many work that OS does before giving the control back to the new process which it has chosen to run on the CPU. Now, when does the process give up the CPU? It can be for various reasons, that it is waiting for some IO, or the process itself says I want to sleep for some time, or it could be that it has exceeded its time limit, which you might have learned about. The time slice is given to each process. If it exceeds that, then forcibly the process will be taken out, because timer interrupt will be running. OS will be maintaining the information that this process has taken more time running on the CPU, so it will be forced out and some other process will come in. So there are various reasons that a process switch can happen. But the problem in this whole thing is process switching takes more time, and in the sense context switch is time consuming, then how can we bring in some kind of a parallelism without making a bigger context switch? Can we have a lightweight process? So that is where the threads come in. Now threads are like a lightweight process. Now what does it mean when I say, suppose our good example is yesterday whatever we discussed, the generator function, which generator function maintains the state of the execution and then it can come back and execute from where it left off. So yes, generator could also be, I'm not, it is not equivalent to a thread, but it is equivalent to that in the sense that we can stop it at any time we want and then start from where we left off, and it is running in the same context of the Python program, right? Similar to that, a thread is something which runs in the context of a process. Then what is the advantage? Now that picture whatever I showed, T1, T2, it is running in the context of a process means we are not doing a process switch. That means the process image, whatever is there in the main memory, they reside there. That when I say image means code, data, stack of this process, and then heap also, whatever if a process specific heap locations are there, it will be, or if it has used the C library malloc, then they may not be. Then all the file handlers, everything, context, everything is there. Now, what if the P1, the process, doesn't want to give up the CPU, but it has some parallelism within the process so that they can actually easily switch between one whenever they want. That means the main image doesn't change. From the OS perspective, it will be like a single process, the same PID will be given, and within that the thread can be running. In that case, what happens is we need to maintain it in such a way that the context of each thread also has to be saved somewhere. Sometimes it will be implemented purely in the software, or OS is also software, but sometimes what happens is OS comes into play even here, and in Linux, even the threads are treated like processes. Okay, but they will have access to the basic underlying process there. Okay, they may use the PCB, separate PCB, but they will not have a costly activities like changing the MMU content and then removing the complete image. If suppose the process image is huge and if main memory is limited, then we may have to copy back to the disk and then get back some other process. So many things are happening there. It's a heavyweight processes. But if threads are there, what is required to be saved as a context is only the CPU content, mostly the CPU content. CPU contents are not meant because registers are hardly some, maybe 128 registers or maybe maximum into 32 bits or 64 bit based on whatever processor is running. Maximum maybe 1K or less than that. The content of what CPU is hardly a few bytes, tens of bytes. So saving this as a context is much easier. So because the main process in which it is going to run remains the same, the context switch between the threads are much faster and more frequently it can be done without wasting too much of time in doing that. So what happens is threads are like they run within the context of a process. So thread cannot live without a process underneath, and they have access to all the contents of the process. So it's like a sibling, like a sibling in our house, brothers and sisters, we share the house, whereas the outsider is like another process. They cannot share whatever we have in the house. So similar to that, a process and all these threads, they share the memory, even the files which they have opened, they can share, even the data that they have, they can share. But mostly the threads will have a separate stack for itself because they may have a different sequence of execution. Functions are being executed. They may have a different stack, but mostly the data and other memory code is also common. They are shared, and there is no access permission blocks will not be there. So main memory doesn't have to be too much bothered about which thread of a process is running, because the main memory will be mapping the same area of the physical memory to the virtual memory of the process. So this is a little bit higher overview of the differences between the processes and threads. Any questions on what I explained? Anyway, you guys are very quiet. You don't want to ask any questions, so I will go forward. My job is to teach whatever I want to share with you. Okay, so threads are there. This is what I was explaining. Let me explain it in a textual form. A thread of execution is the smallest unit of programming commands or a code that a scheduler, usually as part of an operating system, can process or manage. So they can actually switch between threads or context switch can be performed. So OS need to be, mostly threads are not managed by the application. The OS involvement is there always. Even though I say it's a lightweight process, OS involvement is there. And in Linux, in fact, all the threads also have different PIDs, and the parent PID of all the threads will be same, but they occupy different PCB entries in the OS image. Okay. So depending on the operating system, the implementation of threads and processes are differing. Okay, that's what I mentioned. Linux is different in terms of implementing it. More than one thread can be implemented within the same process. So we can, in the sense, more than one thread can coexist within a process. More often, threads execute concurrently. Now, what if I have a multi-core environment? Then maybe we can allow one thread to run here and another thread to run on the CPU, core 1 and core 0, though they belong to the same process. So that means both the cores will be accessing the same memory in the physical memory, but they have a different cache, because now we know that each core is also having a different cache, L1 and L2 cache. So maybe this core thread is executing this part of the code and this is executing this part of the code. They will be accessing them and putting it in the cache, and they run in the CPU. This also can run in parallel. So threads can be running in parallel if there are multiple CPUs or multiple cores in it. Now, one more thing which you might have already learned about, even the CPUs have hyper-threading, which is a architectural feature of Intel processors, which is now being followed by many CPUs. So even if I say core 0, only one core is there, and then another core is there, core 1, both core 0 and core 1 can have a capability of running multiple threads. That means at the hardware level, they have a different set of CPUs, two set of CPUs, registers, and the ALU, and maybe some modules like floating point processor or multiplier, all those things can be common and shared between the different threads, but they have a capability to run multiple threads within the same CPU. In that case, they have different set of registers and they execute different programs in it. In that case, you can have, if you have a two core, which two threads each, then you can actually run four threads at a time. That means they have a separate CPU inside. So, core 0 is different, and the multi-threading capability within the core is different. So this is a hardware level parallelism. And what we are talking about is a software level parallelism. These threads and processes are software level parallelism. If you have a two core, multi-core, and then within the core you have multiple thread capability, hyper-threading, then it's a hardware level parallelism. Okay. So the OS needs to be aware of all this. Of course, they need to, and they will map the processes to the CPU, and they keep track of which CPU is running which thread, and they take care of saving the context and then restoring it back. So this is a quick summary overview of what processes and threads are. Now, multi-threading, and you are all aware that we have multiple priorities and time slice I mentioned. So they run for a while, and based on various reasons, they can switch between high priority tasks. If some high priority tasks become ready, they were waiting for data and it is available, then OS comes into play and they forcibly remove the low priority process and bring the high priority process. So multi-threading can primarily be achieved in two ways. In single process system, multi-threading is typically implemented via time slicing, a technique that allows a CPU to switch between different software running on different threads. In time slicing, the CPU switches its execution so quickly and so often that users usually perceive that the software is running in parallel. So in a single core, at a time, only one process or one thread can run, assuming that there is no hyper-threading feature, but we get a perception that all of them are running in parallel because they run at a gigahertz range, and we expect it to get the output in much lower rate. So we don't feel the multiple threads are even though they are not running, we get a feeling that they are running. Now let us talk about threads in Python. Now what is the threads here? Now when we know that PVM is what is running our Python code, and each that PVM is nothing but an interpreter, okay, which is understanding the byte code and then trying to understand your Python code. So when we run a Python program, a process is created which is running this, including this interpreter, and Python program is executing it. Now one by one the bytecodes are executed, and bytecode is converted into assembly program of CPU, and then they run on the CPU. So this itself is a process. Now when we create threads, it will be running in the context of the process. Then the interpreter is same, the PVM is same, and then they will be sharing the data, and you can create a thread. Now again, this is also very implementation specific, and different libraries like Python version 2.4 and above, okay, they had a library called thread, and then later on threading was introduced, okay, which is having some advanced feature. Now what we are going to use is, because we are in 3.3.88, so we'll be using this library, so we are not going to talk about this now. There are many things that you come across about the Python specific details about threads. I will talk about that later on. Okay, today we will just focus on what I have taken up for threading and show you some examples before we end the class. Now this is one example. Okay, let me show this only. Threading is a library module we are going to use. Now we know that when a process has to start, it should know where to start. Okay, where to start. Like when our C program starts, main is the entry point for our C program to start execution. Similarly, a thread needs a function which is normally called target, a function which is to be executed as a thread. Now what if this thread, the function comes out, ends, if the function is returning, what will happen? So normally many of the real-time operating systems, they say that whatever function you give should never come out. It should be in a while loop and it should never come out. In the sense, because it is an independent thread and they cannot, they have no place to come back again. Okay, I will tell you why is there a limit or a condition that it cannot come back. Now suppose if you are writing a Python program and then you call a function, our Python function, then you say print something, and then you say print here. Now this function, when you call def function, it when it completes, it has a place to come back to. Okay, there is a return address where it can come back and execute the remaining instruction. This is because this is one single process within which one function call is made, and then it is supposed to come back, and after the function call it is supposed to execute. But that is not the case when we are creating a thread. What is happening is, we are creating a thread means we are giving birth to another child or a baby. Then it is going to live as an independent entity, though parent will be there and child relationship may be there, but they live their life in an individual way. It's not that they go back to the parent, right? They cannot come back and then start executing what was after that creation of the process. So they cannot come back because that reason. But in Unix or Linux, we allow it to come back to inform the process, saying that, inform the parent process that what has happened with the child process, whether anything has happened, any error has happened, whether termination was proper. So all those things are there. So we can communicate back to the parent process, but control will not come back saying that all this execution is done and then you start executing the remaining thread in the process, okay, of the parent process. So that is not going to happen. So here what we do, we are writing a class thread, and then this is a method. I will tell you the example, and then init is the first thing, like any other class, which will be called, and then it is the thread class is a that is what I mentioned, that it has threading is in implemented using thread, which was previously there. So it is actually creating a thread here, and then run is what is executing, what is going to be executed as a function. And what is it executing? It is executing this particular thing, and after this execution it is supposed to come back. So let me show you the code rather than explain it here. That will be clearer for you. So let me show the code. Now that is better. Okay, let me. PPT will be difficult to understand the code. Okay, so now let me start off here. We are trying to create a thread. This is the name of the thread and two parameters, three more parameters I am passing. Now let me tell you what is it. It is going to come here. Now when I create a my thread object, it comes here. I am giving the name of the thread and then some delay parameter and initial count, and how this initial count should be decremented, that step I am giving. Now it is all copied here. In the thread itself is an object, so they are maintaining the object. So it's a individual entity and it is maintaining its value. So when we do this my thread, actually the thread is not started running. It is just created. The object is ready. The thread object is created and it is ready to run, but it's not yet started running. Okay, remember we are running this thread in the context of this Python code, which is a process. So what is executing this print and this are like a separate process as far as the OS is concerned, and we are trying to create a thread inside the process. So that's what we are doing here, and we have not even started the thread. We have created a thread object now. There we start. Now let me take out some more. What we do here, we are creating another object, thread object. We change the name of the thread, and then I'm starting with the initial, this values are different. Okay, let me clear this off. Okay, now I'm passing some different values. We will go to the content once we start running it. Now I'm starting the thread. Now what does it mean? Here you see that once I start the thread, what happens is the thread object which we created, this object or both the object, this object, we are calling the method of that, which is actually calling the run. When you call the start, it also calls the run function. Okay, remember that start followed by run. It is internally handled by the thread implementation. So we can either start separately, which follows with the run. I'll tell you the difference between the start and the run shortly. Okay. Now, remember when we start, it actually calls a different method which is defined within the thread function, which is not shown here. It is implemented already in the thread object, thread class, and it calls the run method. Now, run is, we have overridden, and we are saying that this is what my thread to execute when the thread object calls a run function. So I have overridden that, and then I am implementing this. Now what am I saying? Starting the thread. So I said that start will call this function. So this is getting printed and we get the name, and I am calling a function within that, within this. Now what is this function? This is the function which is called within this. So it is in the same context of the thread. It runs this. It is nothing but maintaining a while loop and taking the counter, which is nothing but the init count, and keeps decrementing it and printing the value. So it sleeps also. So it sleeps for some time. That delay what I passed to the creation is coming here, and then it is passed to this. Now what happens is this thread actually it is shown as if it is continuously running, though you are not sensed it because it has slept for some time, which is 0.5 seconds. So we will not be able to really gather that. So it slept for some time, then it printed 5, then 4, 3, 2, 1. Now it stops there. Okay, this function is done. Then finish thread. Then this thread is done. Okay. Now I'll tell you what exactly happening underneath. Okay. Right now we saw this output. Okay. I hope you are able to connect with the what I have done. Start calls the run automatically internally, and the run has completed its complete run now, waiting for 0.5 seconds, then outputting it, and it is decrementing 5. Now let me take out some more code and then show you what happens. So I'm sleeping here. This main thread is sleeping. So I am calling this as a main thread. Okay. Immediately after starting, I am sleeping for 0.1 second, whereas this inside this thread A is sleeping for 0.5 seconds, whereas this is 0.1 second. Okay, actually comment is wrong. So let me, okay. Now I am starting the thread B now. Okay. Now what do you expect to happen? Will this output of thread A and thread B will overlap, or will the threads, all this will be completed and then B will be printing? So if you imagine something, I leave it to you. I'm not going to ask you, but think whether will it be all thread A will be done, or thread A and thread B will be interlaced. Okay. Now let us see now. Okay. Now what is happening? Let us try to understand it. I created both the thread, and the timing is important here. What sleep time? This is thread A is started off. Okay. It sleeps for only 0.1 second. Okay. And then starting thread B, that you saw the printout. Then thread A countdown starts. Now you cannot exactly estimate. Okay, some things may happen based on the implementation. Now I will tell you, after this print has happened, what is thread A is doing? Thread A is in the while loop, and then it is sleeping for the delay which I gave 0.5 second. So this is like a re-entrant code. Please remember, this is a re-entrant code. Multiple threads are going to be executing this function because both thread A and thread B are executing the same method, but they come in with the different values which are in the stack, and they execute it in parallel. So this code is being executed in parallel, and there is only one image of this code will be there in the memory, and both the threads are executing it. Now you see here, count 5. It prints the first value because it started off with 5, and then it sleeps for 0.5 second. During that time, B is ready and it is coming in, because after the start, run is going to be called anyway. So that thread is executing it. Now it executes the same method, prints 10, and then again it sleeps for some time. Now for a while, both will be sleeping. Okay, there is an overlap, so there will be sleeping, and then this wakes up after 0.5 second. It prints 4. Then this wakes up, it prints 8 because I have passed the step as a 2. So it is getting decremented by 2, whereas thread A is decrementing it by 1. So you see that the values got getting mixed up because I have given the same delay. So one here from A once and B once, then A and B and A and B. So then of course A will finish first because the delay is same and it has started early, and then B is printing the last value and then it is also finishing. Both are taking 5 rounds because one is starting with 10 and then going by 2, whereas this is starting with the 5 and going by 1. So 5 prints it will make and then they come down. Now I hope this execution is very clear to understand. Now you may wonder, why did I put a delay? I just wanted to get this after some delay. Okay, I don't want both of them to start at the same time, because then you will get a mixed up output in the screen. That's why I put a 0.1. Otherwise, there is no need for this. Okay, now let me show you one more function which is useful in implementing threads. Now, what is this? Remember, when I started off this through two processes, what is happening to this program, this Python program? This program itself is running as a process. So this also has life in it. It runs. Okay. Now, after the thread B starts, there is nothing much to do. So it is here. Otherwise, what we can do is we can make this process to wait for that thread to complete. That is what is called join. Now, what does that mean? This function call is called on the object thread A. That means it is called on the thread A object, and called by whom? Called by this process which has created the thread. So let me explain with the picture. The main process which is creating thread A, let me say thread A, is starting off something here, and then it is creating a thread B. It is starting off something here. Now this guy has its own life. Now when I say thread A dot join, then we are asking this life of this thread to wait. Okay, we want this to waiting for some event. What event? When thread A finishes its run function. Okay, when the run function ends, when it ends, I told you that it cannot come back, but here it can inform the parent process that I have done my job. A says that I am done. So if the main thread, this thread is waiting for it, then it will be notified, it will be woken up. It's like the parent process starts off both the threads and then waits for the one of them to finish. So join means it is waiting for this thread A to finish. So what happens here is it will wait. How long will it wait? It will wait till finished thread A comes, because thread A, finished thread A will come when this while loop is done. 5 times it is done. Otherwise it is sleeping inside. So thread A is still running. So after this 5 iterations, when it comes out of this count, and then when it says finished, that means the run is done. Now once the run is done, because we started off as a thread here, okay, remember this is a thread, because we started off with a thread function, this end of this run is notified to the parent process. Now which is the parent process? Who has created this thread? Who created it? This program created it. So if in case you execute this method join, then this is waiting for the notification that thread A is done. So what will happen in the printout? Now what will happen in the print? It will say waiting. It will say starting the thread B. Okay, starting the thread B. Then it could be that you see this print first, or you could see this print first. Okay, it depends on how the scheduling of this happens. Okay, sometimes Linux, what does it do? It, whatever new process created, it will give a control to that process, the child process, most of the time, because you may run an exec command there and then you create a new image. So It depends on how the scheduling of this execution happens, but let us wait and watch. Once this print comes, we will not see this print at all. This print will not come until we see a finish thread A, because thread A has to finish, then inform this guy, then it will say thread A is finished. It will again tell you, but already you will get the finish thread A message from the thread itself. Okay, or I can say I am coming out. Okay, instead of saying that I am coming out. Okay, we can say that. Now after that, this will be printed. By the time, what will happen? Thread B has already been started, so it will be running also. So you will get those messages, and then immediately thread B also would have completed by now, because both of them are finishing at almost same time. So you will see that the thread A and thread B join may happen one after the other. So let us now, let us not remove these messages. Let us run it again. Now we'll see what does that we see here. Now main is going to wait before that thread starting thread B has come. That means the control from here, when you say starting the thread B, then thread B start. When it executed, it went there and it executed that, and you got the print of this. Then it went to sleep. It is not even printing the first value. Before that, this main is coming. So it is switching between these two. So you see this print. Now, once you see this print, what happens to this thread? It is going to wait. It is not going to execute this further. It is waiting here for thread A to finish. So now thread A is printing this. Because we already started thread B, that is also printing here. Then they alternate between them. And finally, when thread A finishes, then main is woken up. It says that main thread A finished. Then it says I am going to wait for B. By the time thread B is not even printed the last value, so it prints the last value, it finishes it, then it wakes up this main thread, and then it prints both threads are finished. So this is the sequence how join happens. Okay, if in case if you had a system programming course or Linux course earlier, you may be already aware of all these things, whatever I have told. If it is new, maybe it will be useful. Okay, I always assume every one of the class members should understand it. Okay, that's why if you get bored, I cannot help it. I cannot assume that everybody knows it. Now, again, I would like to ask you if there are any questions. Okay.
That to join only we can join to the main thread only.
I'm sorry.
Like if I want to join with A to B, not the main thread, then I can do.
Okay. Very good question. Okay. See, this is join is for the thread A. Because you are calling the thread A. Suppose this notification can come to the parent only. Okay, let me, okay, what you are asking is, can parent B, the thread B can say, I want to join thread A. Now, how will you make it? Now, let me tell you, this object name, first of all, this object is not available to thread B. Okay, even if you want to call it, how do we call it? Now, it has to be called in the context of thread B. Now, thread B is executing either the run, okay, this program, or this function. Okay, it is executing only these two. Okay, now if you want to actually make for example, you want to make thread B. Okay, um, okay, let us say thread A is first running, right? So thread B to say that I want to wait for thread A to join me. Now we need to pass this object. Okay, it depends on the implementation. They, in my opinion, Python wouldn't have, like, no, be very much concerned about that. I will, if you have time, we can try it out. Okay. Now, it is difficult to do because we are using the same thread. Okay. We are using the same function, and both of them are running the same function. So, if you want to do it, we need to somehow, I hope you understand that this object, if suppose you want to call thread, I want to join for thread B, that from thread A. Okay, let me explain. Okay, maybe I don't know whether I'm making sense. See, you have a main thread. The main problem here is, first of all, implementation. Second question. First question is whether.
Sir, your voice is
Breaking. Okay, I don't know whether. Oh, same
sir,
problem.
charging.
Oh,
Sir,
I think.
charging problem.
Thank you. I do the same mistake. Sorry. I hope this is solved now. Okay, so let me explain. We will not try to do it now. Okay, maybe we'll reserve it for Monday. But this is an interesting question. I said that a join is there. Now, if I want to do that, I need to have this thread a object available to me, which is there in main because I only created it. Now, suppose this is the a and this is b, and I know that A started first. So B actually can say, I want to join A. In the sense, B is alive by the time J would have been finished. Or I can even say that delay is 0.1 second here and delay is 0.5 seconds here in the while loop. Then this is going to take more time, okay, to die, suppose 5 iterations, whereas this guy will finish it off much earlier and it is coming up first also. So this will be finishing first. Now I want to call thread B join, sorry, A join. That means what? I want to say from this context, I am waiting for thread A to come. I want to wait here. Okay. Now I don't know the answer for this, whether it is allows or not. But the before even checking it, we need to make sure that this object is available for thread B, which is a bigger thing because we need to create it here and somehow pass it to this. Is because I said that process and threads are accessible. You may wonder that maybe I'm available. This thread A is available here, so that is also possible. But let me say, just try it out. Okay, why not?
Sir, one confusion.
Yeah.
Can we create a thread inside the thread execution?
Mm, yeah, we can do it. Okay, this is also another thread only. So let us try it out now. Okay, now first of all, if I use the thread A, does it accept it? Okay, it accepts it. Now the problem here is thread, it will be in an infinite loop. Okay, because the same code is running and you will have a thread A is also running the same code. Okay, we will have an issue here. Okay, the same class we cannot do it. We need to write it in a different way, that I have to have a condition that only if you are a thread B you call this function. Okay, otherwise thread A will wait for thread A, which is runtime error. It will give an exception saying that no, otherwise it will go into infinite loop. I hope you understand that. Okay, first of all, it allows thread A. Let us see whether compiler gives a problem. Now see here, runtime error happened because you are waiting for a thread, for the thread which is thread A is also going to wait here. Okay, that's the problem here. So this needs to be handled separately. I will explain that in the next class. Okay, I don't know who asked the question. Who?
Nanisha.
Dhyanesh. Okay, I will. I'll resolve it because we are running out of time. So okay, let us. This is only a first example of how the thread and join are working. Okay, so let me see whether this code is clear now. Okay, I should now modify it. Okay, I will add more things on Monday, and then we can still verify all these things about the specific implementations of what is allowed and what is not allowed, and if there are any issues, I will tell you that. Okay.